Hi, welcome to our first video for 5.6 modeling sinusoidal phenomenon not using angles. So in our last section, we looked at like a Ferris wheel and some other applications where angles were involved. In this section, we're just going to look at real life scenarios where we're not using angles at all, but we can still model the behavior using a sinusoidal function. In our first example, we're going to look at alternating current. The electricity used in most of the world is alternating current, unlike the electricity from a battery, which always flows in the same direction. AC electricity reverses direction in a cyclical fashion. So with AC current, the electricity will flow this way at one moment and then it flows back the next. The number of cycles per second is not the same in all countries. In Canada, the United States, and some other countries, the frequency standard is 60 hertz. That means 60 complete cycles per second are completed. So if the AC current's going this way 1 second and then it switches the other way, well, if it's rated at 60 hertz, that means it does that 60 times in 1 second. So you've probably noticed this with maybe some of the fluorescent lighting in buildings. You can sometimes tell that it's flickering, and it's because the current is actually changing direction 60 times in 1 second. So also in Canada, the maximum voltage is about 170 volts, and the voltage can be modeled as a function of time using a sine function. So we can see this nice equation right here. We have V for voltage. The voltage is equal to A for amplitude, sine, and then KT minus D. T would be time in seconds, and then plus C. So we're first asked in this example to find a period of 60 hertz AC. So we can put our solution off to the side over here. So we're looking for the K value for 60 hertz AC. So that's actually a frequency, 60 hertz, okay? And that means it actually does 60 cycles per second. So the symbol for frequency is this F here. So F would be 60 cycles per second. So period is related to the frequency. Period is actually the reciprocal of frequency. So when frequency tells us the number of cycles per second, the period tells us the time for one cycle. So we can go ahead and find the period. We're just going to do 1 over the frequency. Okay, and the frequency is 60. So the period is just going to be 1 over 60. So that's the period. Now we're asked to, that's for part A, the period. So it'd just be 1 over 60. So, and this is time based, so it's 1 over 60 seconds. So if you want to get a number for that, it would be close to 1 divided by 60. It would be close to 0.01 and then 6 repeated. Okay, so it's obviously a very small number. And notice the current changes direction 60 times a second. So each cycle has to be really, really small. Okay, that's what we have there. All right, part B, determine the K value for the equation. So remember, K is equal to 360 over the period. So that's going to be 360 over 1 over 60. Okay, if we're dividing by a fraction, we need to flip and multiply. So we'd have 360 times 60 over 1. So that's going to work out to 21,600. So that's our value for K. I'm just going to write it again. That way we can easily grab it when we write out our equation. Part C, what is the amplitude? So for AC current, the voltage at a maximum is 170 volts positive. We'll write max there. But when it changes direction, it actually changes sign and it becomes a minimum value, negative 70 volts. So this voltage fluctuates from a max of 170 to a minimum of negative 170. So it's kind of easy to find the amplitude from this. The amplitude will just be 170. All right, part D, model the voltage with a suitably transformed sine function. So the voltage is going to equal the amplitude, 170, times sine. The K value we found to be 21,600. And then we'll put T for time. And then we'll close that up and write plus C. So this is all we have for now. We actually don't know D or C. So the nice thing when you're trying to model voltage, if the max is 170 and the minimum is negative 170, that means that C should be equal to 0. So we can tell that the middle value between these has to be 0 because they're like positive 170 and negative 170. So we now have a value for C. That's good. And now the next thing is D for a phase shift. So the thing is, we're not actually told what this voltage begins at, so we don't know if we should do a phase shift or not. So we're actually just going to leave it blank, which is totally okay when we're modeling voltage, because as soon as the cycle starts, it's going to keep changing direction anyways. So our final equation just involves the two parameters, A and K. And that's it. All right, I think the next part is going to ask us to graph it. Yeah, it says use technology to graph the voltage function over 2 cycles. Explain what the scale on the axes represent. So let's put this equation in here. Y equals 170 times sine 21,600 x, and then close the bracket, and then make sure we're in degrees. Okay, we got a blue screen, so I'm not surprised because the period's really small, right? So let's open this up more. There we go. Okay, so there is 2 nice cycles. So notice there's no phase shift, so we're beginning at the origin and going up to a maximum, and we can see that would be 1 full cycle, 0.01667. That was the period that we found. Okay, and our max is 170, our minimum is negative 170. So we can see this equation works really well. What would the scales be? So I guess we could say like the y-axis is going to be voltage, and we probably want to go from, negative 200 all the way up to 200. So for the y scale, okay, this is voltage. We're going to go from negative 200 volts to 200 volts, just to see, the nice sine function here, right? We don't want to just go from 170 to negative 170. We like to see a little bit of space above and below. And then the x scale, if we want to see 2 full cycles, so this is time, okay, we could probably go from 0 seconds, and to get 2 cycles, we would have 2 over 60, because remember that's 2 times 1 over 60, that was the period, 1 over 60. So if you have 2 cycles, adding those up, you get 2 over 60, which actually simplifies to 1 over 30. So we want to go from like 0 to 1 over 30 seconds. Okay. And also, if you wanted to graph it too, I would probably, to show 2 cycles in here, I'd probably want to chop everything up into 8 pieces. So if I had to pick a scale, like intervals, I'd probably do 1 over 240. Okay, because 8 of these would bring us all the way to 1 over 30. It says 1 over 240. That would be like a good increment to use. Okay, that's it for this first example. I'll see you guys in the next video where we take a look at example 2.